In yesterday's class, we were looking at how Newton's laws end up being used. So for particular examples that you get, you may be asked to write, explain, describe, and you may have to use more than one Newton's laws. Normally it's Newton's first law with the third law, or Newton's second law with Newton's third law. And we were looking at again acceleration and what it takes to cause an acceleration. And here's another example. Just like the water in the cup, you can also look at now this only happens just for that moment. You can look at the position of the rope starting and stopping. You accelerate first. So you see this. So if you had the ability to record this, you would see that as I move this part, this is not ready to move either, right? So the position of the rope will be like this. And then when I decelerate, it takes that position. So acceleration means the rope must take this position because this is a stopper. It's not ready to move. It doesn't want to move. Object remains at rest. Objects that remain at rest want to continue that state of remaining at rest, right? So acceleration is what is produced by resultant forces, and this must, if this is to start moving, it must accelerate first, and if it is to stop moving, it must decelerate. So starting from this side, you may not be able to see this, but the best way is to look at the water in the cup, or so many situations where you have parts of the system trying to stay behind. So when the top part moves, that top parts here, as that accelerates, this is not willing to accelerate, but they're all connected together, so it has to comply later on. So how does this part, if the top part accelerates that way, how does this accelerate later on? Well, because of the rope and the tension in the rope will provide the required resultant force by taking that position. So the tension acting this way, you have components. There will be components horizontal and vertical as well. So back to looking at components as well. But I'll start off with the water in the cup and finish that off. And look at the rope and stopper, and then look at some other examples similar to this. So the water in the cup, and I said the water has no choice but to move with inside, it's inside the cup. That's a basic thing to know, but of course the water, if you move it too quickly, it might spill out. So it's trying to get that larger resultant force. So the faster you move it, the more you accelerate it. Now you can accelerate it in different ways, right? So the more the acceleration, the water inside the cup requires more resultant force. So then it takes the position, and in some cases it might spill out also. So that's when it won't get the required resultant force. So let's see how to explain. Well, what would be the question? Explain why the water takes this position. Explain why the water takes this position. Which way is it moving? But this same position can be obtained by the cup moving this way and decelerating. That typically what happens to you if you're moving in a vehicle. As the vehicle starts to move, your body is reluctant to move, so you think you're getting pushed back. When no, you're also now having to move with the vehicle, and by getting pushed back onto the seat is providing applying a force on the seat, and the seat applies a force on you to move inside the vehicle with the vehicle. Get into a bus, you better hold on to something, because that's the best situation to experience the water in the cup. Because in Sri Lanka, you get into a bus, the bus driver accelerates as if he's starting a race. So you better hold on to something, because you need that resultant force. If you don't hold on to something, then what happens? You don't get the resultant force to move with the bus. So you get left behind. That might cause you to slip and fall. All right. So let's look at this one. Acceleration is to the right. The resultant force on the water has to be, and the greater the acceleration, the more resultant force you need. So the water takes that position. So explain the position of the water, why it takes this position. Do not use the word inertia. There are no marks for that. Do not use the word inertia. The water must have the same acceleration as the cup. Because the water is not going to come out of the tiny gaps. There are no gaps. I don't think there are gaps in glass, but the water won't come out of the gaps. We know that. That's why we use cups. It doesn't leak. The water must have the same acceleration as the cup. Therefore, resultant force should act. Comes from the normal contact force from the side of the cup. But we just call it a contact force, normal contact force, such as what I've indicated this way. So the greater the acceleration, the more amount of water is trying to get into contact with the side of the glass, with the side of the cup or the side of the glass. This is a normal contact force. So the only thing I haven't mentioned here is that this is an application of, I can add it here. By Newton's second law, therefore, the resultant force on the water to cause the acceleration comes from the side of the, it's a normal contact force. So that's how you explain that position of the water. But when you decelerate, you may be asked to draw the position of the water when you decelerate, or when the cup decelerates. And if you've seen it, well, it's like this. If you haven't seen it, well, there has to be some intuition when you are doing physics. If you don't know how to jump, well, try it out. But the thing is, you can read a note on it. No. So a deceleration, if it's decelerating to the right, then it takes this position. You can explain it now because you have this explanation for this. Accelerating to the right, decelerating to the right, you need a resultant force the other way. So that's why it takes that position. It comes into contact with the side of the glass to get that contact force. So, but if you try to accelerate it the other way, also it takes this position. Now there are 4 cases really. And 2 cases you have the same position. That is accelerating to the right or decelerating to the left, you get this position. Try it. Go to the kitchen, get a glass of water, and don't injure yourself in doing this. This happens in 2 situations, decelerating to the right or accelerating to the left. This position. Let's look at the pendulum one. But there are so many examples. In fact, you would have experienced all 4 cases of this. But in a situation where you were going vertically up and down, in a situation where you were going vertically up and down, can anyone tell me that situation? Imagine a situation you were going up and down in something, inside something. And everyone has been in this. It's a transportation device. It takes you up and down. Anybody?
Sir, lift.
A lift. Now, those who didn't get that, well, you can see how poor you are to have not noticed these things in your life. And then you are expecting me to teach you physics. You are inside a lift. Have you not noticed as it starts to move upwards, it's an acceleration. Everyone has been in a lift. Nobody here, I think, hasn't been in one. When I was 10 or 11, I think 10 or 11, I remember going in the lift up and down. Empire State Building, New York. Empire State Building, New York. You can see it's a high-speed elevator. You can see the floor numbers on the display just flipping so quickly. So you go to the observation floor, right? I don't know if that is permitted now. Even that long time ago, it was just no security checks. You just walk into the Empire State Building, right? That was it. You walk into the Empire State Building. I don't know if we even had to buy tickets. At that time, it was not like that. Now it's a huge tourist attraction. I'm sure you have to pay like $30 or $40 to go up to the observation floor. Everyone has experienced this, and that is when it starts to accelerate, you feel a bit heavier. And as it reaches the top floor, it decelerates, you feel a bit lighter. And then from the top floor, as you go down, you feel lighter again. And as you decelerate, you feel heavier. But then it's similar to this, but this is going horizontally. So accelerating to the right and then decelerating, moving to the right, and then accelerating to the left and decelerating to the left. All right. Let's look at the hanging object. And now you can hang this to the car in front, or you hold it. Next time you're in the car, just hold a pendulum like this and watch as the car starts to accelerate, it comes back to you. It's trying to get the resultant force from the tension in the rope. So this position, the position it takes here could be either accelerating to the right or decelerating to the left. Accelerating to, let's say it's accelerating, just like the water in the cup now. Now you are familiar with an earlier example, water in the cup. So that's now what you're going to base all your ideas about this on, the water in the cup. Unless you can make that connection from water in the cup to this, you have to have some ability to exercise your mind to other situations, right? Otherwise, that is a requirement in the physics syllabus. Be able to be able to attempt unfamiliar situations. So that skill is not so hard, really. I don't think that skill is so hard. I mean, we can recognize a blue color car from a red color car. The color is different, but we know when we see a car, right? We can recognize a ball from a bat. We can do those things as well. That's basic intelligence. Unfortunately, the physics part has now required us to actually give you the intuition that we expect you to already have. Now, it's going to be very difficult for me to discuss those things and convey them unless you already have that ability, those skills. Not that you need to have known everything about jumping, but then I just filled in that requirement in the syllabus. Everyone knows how to jump, but we never really analyze the forces, right? So that's what I did. I can't help you to jump in the first place. That's something you would have done before. The tension in the rope, how is this similar to jumping? Well, the resultant force, this pendulum will have to accelerate the same way as if it's hung to the ceiling of a vehicle. It will have to accelerate. Eventually, it will have to accelerate the same way. Otherwise, it will be left behind, or it won't get the required resultant force. Therefore, it will stay the way it is. You can use Newton's first law as well. You can say, well, an object remains at rest unless there's a resultant force, right? So there is a resultant force here, and it is a component of the tension. What are the other forces acting on this? You have the weight. Now you're going to say, well, look, isn't there a backward force? Otherwise, no, there's no, this is acceleration. There can't be forces to balance here. You cannot have another force acting this way. It doesn't exist. And that's what I was doing here. Where's my, it may not show up on the, this was what I was showing. Maybe this one. The fact that this eventually does start moving, but you can see that it takes a position. Not show the whole thing because you'll get confused if you see the whole thing. You hang this or you hold this, and you will see as I accelerate from this point, if I accelerate this way, it takes the position like this. With the tension is giving the resultant force, a component of the tension. So now we are learning about how components are providing the resultant force. By the rope being in a slanted position, by the rope being in a slanted position, the tension is at an angle. So then there are components. Provides the required, and there is a math part here we'll do. So you need to copy this, you need to copy both, because this is at rest, but there's another situation where you will see this in this position, and that is when it's moving as well. Can someone tell me how can this be in this position and what that particular motion has to be? When it's moving in a certain type of motion can also cause this to hang vertically. So I'll say at rest, or what? Or what?
So, is it constant velocity?
Moving at constant velocity, left or right?
So, right.
It doesn't matter. The direction doesn't matter. All right. So whether it's moving to the left at constant velocity or to the right, it will have this position. It will take this position at rest or moving at constant velocity. And the direction doesn't matter for constant velocity. This position definitely can happen in two ways. Well, I'm assuming that it's accelerating to the right, but also it will take this position when it's decelerating to the left. Provides the required resultant force by the rope being in a slanted position. The horizontal component of the tension provides the required resultant force for the, call this the pendulum, the mass, the object, whatever you want. Let's say it's a pendulum. Bob, pendulum bob is what we call it. To accelerate, and that is Newton's second law. And then what we can do is, if you have this angle measured, the angle with the vertical measured. Now this is one thing that a lot of you are too lazy to do. They don't realize that you have the same theta angle here. That is your laziness, because that is not a physics thing. We are using corresponding angles. I can't remember what you call them, but I know that this angle, this vertical line, is another vertical line. They're parallel, and these two angles are equal. So we have the T sine, that is the horizontal component, is T sine theta. The vertical one is the cosine. So you can always go with the cosine. And once you've done that, say, well, the other one has to be sine. So here's that other one, T sine theta equals MA, and take the mass of that pendulum. But then there is strangely enough, you're going to say, well, look, this I can't believe, but you actually have vertical equilibrium because the pendulum bob moves at a constant height. So you have vertical equilibrium. Newton's second law here, but for vertical equilibrium, T cosine theta should balance the weight. So interesting things happen if the acceleration increases. If the acceleration increases, the theta will increase. So that's there in the formulas. In these relationships, you can now change something. You can increase the acceleration. On this side, the angle can increase. The tension in the rope can increase as well. So if the rope is not strong enough for a particular acceleration, it'll break. This here, this is N1. Do we need to use Newton's third law here? No. So here is a situation where you get two expressions by acceleration taking place horizontally, but you have vertical equilibrium. T cosine theta balances the weight. Why? Because this is going at a constant height, but accelerating to the right. You can do one more thing, and that is divide the two. The T will cancel, the M will cancel. Now, this was something that came in a past paper some time back. When you divide the two, divide, and I've conveniently written it, so you just divide here. The T will cancel. You get tan theta is the M, the mass will cancel as well. All right. And then what does that get you? Acceleration is the acceleration depends upon two things. It depends on the acceleration due to gravity. You increase the acceleration, your theta will increase because you see tan theta. Let's move on to this one I'm doing simply because there was a past paper question on this, where the components had to be used. You had to use Newton's second law, first law, and know by mathematics that if you divide this, there are some cancellations. Now it's not physics that told me to do the division. It's by seeing expressions and relating it to what we do in mathematics. All right, the sine, cosine, oh, if I divide them, it's something that occurs to you by being familiar with mathematics, really, not physics. All right, so the last part here is to do with being familiar with techniques in mathematics. But then in the end, you go back to analyzing and using your knowledge with physics, and that is G is acceleration due to gravity. So then you think about the fact that, well, your acceleration here depends on those things. So you start with physics, you go to mathematics, and you end up going back to physics as well to analyze, interpret the final result, because it should mean something. What are the other examples? Up and down, elevator, up and down. So this, I think I've given you enough time to copy this. But there's another position, another situation that this will be like that, and that is decelerating to to the left. So you decelerate to the left, then you imagine yourself in your car. If the car suddenly brakes, you end up going forward because whatever is moving wants to continue moving. But you will have to produce, you will have to from somewhere, you'll have to get a resultant force. So you continue moving until you hit something. Or you hold your hand up to the seat in front or the dashboard in front to get that resultant force so that you decelerate the same way as the car. You're in the car, you need to move with the car inside it. So if it accelerates, you have to accelerate with the car. If the car decelerates, you have to decelerate the same way. So if you keep your hand to the dashboard, if you have seat belt, they provide those resultant forces for you to maintain your position in the car, right? But it's by increasing or decreasing certain forces. So let's look at the elevator. Let's start from the ground floor elevator or the lift. So you're at the bottom here. The best thing to analyze this is to take a weighing scale and put it on the ground and stand on it and look at the changes. A weighing scale is also an interesting thing to discuss. So I'm going to say a weighing scale. You're inside the lift, you're standing on a weighing scale. In a rest position, weighing scale can only work in a rest position. Otherwise, they will not give you the correct reading. If you start to accelerate, the weighing scale will give you a larger value. You're going up, as you're going up and you start to decelerate, the weighing scale will give you a lower value. Why does that do that? Isn't the weighing scale measuring your weight? And doesn't your weight not change? Your weight doesn't change, but the weighing scale doesn't measure your weight. Can anyone tell me what force the weighing scale needs to be activated? What is the force? What is the correct force? What type of force does the weighing scale need? I can give you a hint. Obviously, you have to get onto it. You have to get onto it. Otherwise, it's not going to. So what is the force that you're exerting? What type of force? You get on, you make contact. No, so you tell me what the force, what is that force?
So is it normal contact force?
Normal contact force. So you have to get onto it, otherwise it won't show your weight. It's a contact force. And when in a rest position, the weight equals the normal contact force. So the weighing scale actually measures the contact force, and in a rest position, since they're equal, you're measuring your weight, but then it's given in kilograms, right? Not in newtons. But fine, I'll refer to the value shown on that scale in kilograms. We'll call it the weight. You can calculate the weight by multiplying by 9.81. But you are exerting a downward force, right? and what you're exerting is equal to your weight. It's a reaction force. So otherwise, there's no point. I mean, you have this, equilibrium, you have a table. Wouldn't you have put weight and normal contact force and say they're equal? So if you want to measure the weight, you can measure the normal contact force because they're equal in a rest position. But also your weighing scale will also function properly if you're moving up or down at your weighing scale will also show you your weight correctly if you're moving up or down at what? At what motion? What motion should it be? When will it also work as you're moving inside a lift? If you are moving at
the constant
velocity as well, it will work properly, but not when you accelerate. Then it won't work properly, right? Because you need a greater reaction force, and the weighing scale measures that reaction force, so it increases, and that's what you feel. Also, you feel heavy when the lift starts to accelerate. So I'll go through this example. When the lift starts to accelerate now, so all this discussion has now come to this. When the lift accelerates upwards, you're in it, you also will have to accelerate the same way. Therefore, you need a resultant force. Believe that to accelerate, you need resultant forces. To decelerate, you also need resultant forces. So you have to have the reaction force. I'll put it like this: reaction force. You also have the weight, but the reaction force is greater. Otherwise, you don't get the resultant force. I really can't go back to explaining what a resultant force is, because in year 9, we teach you what a resultant force is. To teach you that we say 2 newtons that way and 7 newtons that way is a resultant of 9 newtons. 7 newtons this way and 2 newtons that way is a resultant of 5 newtons that way. I really have just taught you that anyway. If some of you are blank on resultant forces, you have to somehow get that sorted out yourself. I can't really go back to those things, but I just did. In fact, I went back to the year 9 lesson where we teach you resultant forces. You need a resultant force to accelerate, and it's only going to happen with the reaction force becoming larger than the weight. That's why you feel heavier. What you feel as your weight is actually the not your weight. So the only time you feel your own weight is when you're at rest or when you're moving at a constant velocity up and down. When you're accelerating, you feel heavier. So then you will have to realize, am I getting heavier? How come I get heavier? How come you feel this? Because you're feeling the reaction force, not your weight. So all this time you've been walking around, and whatever you've been feeling as your own weight is actually a different force. It has been the reaction force acting from the ground all this time. So the reaction force is greater than the weight. Then you get the resultant force to accelerate the same way as the lift. If you start decelerating, so let's now go to the next part where you start to decelerate. What happens then? So you're still on the weighing scale, and as you start to decelerate, you'll see the weighing scale reading a lower value, lower than your weight. minus A. You're going upwards, but you're decelerating. The weight is the same. That doesn't change. I'm not marking them in the right places. You're going to get confused. But the thing is, I'm labeling my forces. W is for weight. Okay. Some of you will, I know some of you are completely lost. But I'm sticking with two forces. And I'm saying that the weight of the passenger never changes. And I shouldn't need to tell you that. Right? Unless you're eating something while you're moving inside a lift, then, or you take off your whatever, you cut off your hand, and you can say your weight changed, right? The weight is there. Let me just show the weight here, and the normal contact force has to be less. The normal contact force has to be less. And that's why on the weighing scale, you see a lower value, a smaller value, and you also feel lighter. So if you, even if you don't have the weighing scale, you should have noticed this. If you haven't, then I'm teaching you that. I'm teaching you that when you start to move upwards in a lift, that's an acceleration, you will feel heavier. And as it gets to the floor where it's going to stop, it decelerates, you will feel lighter. So I'm telling you that. If you haven't noticed that happening, why? Because you're too busy with other stuff. You don't know where you are. That's why. So whenever, next time when you're outdoors, please notice that you're outdoors. Don't have those things plugged in your ears and fly away to the moon. Know where you are. So here the reaction force is less. So I'm going to write reaction force less than W. Here reaction force greater than W. All right. And if it is moving at constant velocity, somewhere in between, the reaction force and the weight are equal again. Right. So that part is not there, but here acceleration, deceleration. I'm not going to have things written for this, but now you should be able to get that information from the earlier examples to explain these things. Newton's first law, acceleration. The passenger has to accelerate the same way as the lift. Therefore, resultant force is required. The normal contact force is greater than the weight to provide that resultant force. That's the way it is. I mean, the A2 class will be less than half of what is here. That's what I see all the time. The A2 class will be half of this. Let's see who's here. Binudi. Binudi didn't come. Mahathir.
Here, sir.
Yunara. Not here. Nushal.
Yes, sir.
Who else? The others I have got. So the worst thing is to not think about these things. So for that you need the time. You need the time to think about what I said, and then to recollect the last time you were in a lift or the last time you were in a car where you felt these things. If you don't spend that time, well, this is going to get more difficult. The mathematics will not add up to anything. You'll be just staring at just equations. All right. The forming of the equations is the hard thing. Now, let's look at trying to apply F equals ma, where the greater force is R, right? If you have 7 newtons up, 2 newtons down, well, 7 minus 2, R minus W. So you know that without having to have specific values, R minus W should equal mass times acceleration. And over here, W minus R should equal mass times acceleration there. All right. The resultant force is downwards, the resultant force is upwards. So keep in mind those directions. Of course, if you're accelerating upwards, the resultant force is upwards. If you're moving upwards while decelerating, the resultant force has to be downwards. So having said those things, the next example, we've done the elevator, we've looked at how these expressions change, but still this Newton's second law, this is also Newton's second law, but you have to know it depends on the situation. Accelerating, now this arrow gives a sentence, accelerating upwards. So I don't have to write that for you. Unless you don't see the, now that's the other thing. You need to connect with the diagram. Connect with the diagram. You connect with the internet, right? Connect with Wi-Fi, right? So connect to the diagram. Look at these symbols. They're trying to tell you something. Arrows, at least an arrow pointing upwards is a point. It's indicating in that direction. So we have ways of showing forces. We have ways of indicating the direction of the acceleration. Connect to the Wi-Fi, to the diagram. We love to connect to the Wi-Fi, right? But then, unfortunately, it's easy to connect to Wi-Fi than to connect with these diagrams. What's the next one? There might not be a next one. Now, I will tell Mr. Sandharuwan to start with the momentum. Okay, so we'll see you next time.